and it's a okay. It is a really good chance to have a webinar in this task force. Actually, to be honest, I know the title of today's webinar is a little maybe too attractive. I know. In fact, over last 10 years, I did many works on data-driven optimization using evolutionary algorithms. But I haven't done much work on expensive combinatorial optimization. But I think over 10 years, I have some experience which can be shared with you. So let's start today's webinar. So the first thing I think we need to have a definition of what is expensive combinatorial optimization. Yes, so for optimization problem, we need to define the decision variables, objectives, and constraints. So for expensive combinatorial optimization, the decision variable is discrete. But for expensive problem, usually when you calculate objective and constraint, that is expensive. Then combine those two characteristics, that is expensive combinatorial optimization problem. As you know, data-driven optimization problem, they come from real-world application. So combinatorial optimization problem, they have a lot of real-world application. So I can give you some example. So for when you design circuit layout design problem, that is a combinatorial optimization problem. And when you evaluate each layout, whether it has a good performance or not, you need simulate something. So that part, when you calculate the performance, it is quite expensive. And also another well-known expensive combinatorial optimization problem, that is one really, I think, hot problem in last 5 years. It is neural architecture search for deep learning. You know, when you design a deep neural network, you need to think about what is the structure will give you a good performance. So that actually you can put different blocks together. So that is a combinatorial optimization. But you need to evaluate by training that deep neural network. That is really expensive. So that too, I think, can give you an idea how hard it is for expensive combinatorial optimization problem. So as you know, I have done years of work for expensive optimization problems. So to solve expensive combinatorial optimization problems, I think the most straightforward way to solve the high combinatorial budget, that is, you need a machine learning model, we call it surrogate model, to replace the expensive quality evaluation for candidate solution. So that is a basic idea. So I think the most important methodology in today's webinar, that is, you need to build a surrogate model to replace most of the function evaluation during the optimization. Then you need to choose a kind of optimization algorithm to search on the approximate landscape. So because my prior research was done in the area of evolutionary computation. So naturally, I will use evolutionary algorithm, PSO, DE, and so on, to act as the optimizer in those algorithm. Okay, so if you interested in this data-driven evolutionary optimization, you can look into our new, not quite new, survey and book. Okay, so that is the idea to reduce the high computation budget, right? But when the problem is when the decision variable is not continuous, so we need to talk about what is the challenge, what is the hardness, right? So actually, the search on that kind of discontinuous decision space is quite different from previous work. So I think that kind of decision space will give you some hardness. The first thing that is, it is really hard to search. I don't think whether because I'm not good at combinatorial optimization, right? So evolutionary operators are not that good for searching, right? In this kind of decision space. That is the first hardness. The other thing that is, you know, when you build a surrogate model, you need to calculate the similarity of samples, right? So in for combinatorial optimization problem, actually the distance or the similarity is really hard to be measured. That's the reason we don't have high quality surrogate model to do that. So here I list several very popular surrogate model we use in expensive continuous problem like Green model, PR model, RBFN models. So actually, they are not really good for expensive combinatorial optimization problem because of the decision space. The other thing that is for combinatorial optimization problem, that is really easy to have a high dimensional decision space, right? So I think that is a mean hardness. So how to solve it? I have, at the very beginning, I think 9 years ago, I was a beginner of data-driven evolutionary optimization. I go through all the possible surrogate model. I found one. Maybe we don't need too much measurement on the decision space, that is random forest, right? That is a decision tree-based ensemble learning model, right? So it is because of that structure, actually it is can be used for a combinatorial optimization problem. So at the very early time, we think, okay, maybe the only model we can use, existing model we can use, that is random forest, then we need to apply it to some problem. So here, let's use this deep neural architecture search as an example to give you some idea. So as I said, the decision space that we have different kind of block, like resonance block, pooling block, and so on, right? So the encoding of one kind of architecture is you need to combine those blocks. So that is the decision space. And the objective, that is we can quantitative measure the performance of this architecture. So actually, you can use the training error to do that. However, you need to train this architecture. So that takes a really long time, which makes this problem really expensive, right? So based on those 2 points, we think, okay, we can use random forest as a surrogate model, and it is a really simple single objective optimization problem, right? Because we're only trying to reduce the training error. So maybe we can just use a very simple optimization algorithm like using GA. So that is the framework of this algorithm, right? So at the very beginning, you need to prepare the training data for the random forest. So you random sample different kind of architecture, and you train those random architecture, get the training error as a label for random forest. Then during the optimization, we only use this random forest to predict a new candidate architecture, the performance, the training error. So actually, I use some trick because it is a kind of offline data-driven optimization. We didn't do any online sampling for new architecture. So we use a kind of selective binding technique to combine the surrogate model. Okay, so the result is really interesting. So we only use 123 random architecture as the training data for random forest, and use a really simple optimization algorithm to do that. Then we can have a really high good performance on CFAR 10 and CFAR 100 dataset. So I know this accuracy is not that high in the domain of NAS, but this work was done in 2018. So at that time, using this really low combinatorial budget, it is a really good performance. Okay, so that is the first example of expensive combinatorial optimization problem. Then we move on. We have a new, a little bit different real world application. It is a kind of trauma system design in Scotland. So in Scotland, we have several hospitals. We need to assign different kind of level to those hospitals, right? And for the government, we hope trauma system configuration can give you a good performance. So they hope the total traveling time and patient exception and helicopter uses and MTC volume can be controlled by them. So the thing is, when you evaluate those objectives and constraints, you need to allocate patients for over 1 year to those hospitals, which means actually for each function evaluation that is expensive. And this problem is harder than the previous NAS problem because we have multiple objectives and multiple constraints. So the very straightforward way to solve this problem, we need to build a surrogate model for each objective and each constraint. Yes. so in this case, we still use random forest, and because that is a multi-objective optimization problem, so of course we just use very famous, very popular, easy using optimization algorithm NSG2 to solve this problem. And a very important issue for this problem, that is we have multiple surrogate model for. So in this case, we have 2 surrogate model for objective and 2 surrogate model for constraint, and we feel the accuracy of random forest is far from satisfactory. And what's even worse, that is, the error on the constraint will mislead the search seriously. So because of this issue, we have done many strategy to correct the prediction for whether the solution is feasible or infeasible. We have done several tricks. For example, we use this logic regression to change the constraint binary to make more solution can be predict correct, and so on. So here is an example. So if we firstly apply this algorithm to the Scotland trauma system. So there are only 18 hospitals. So from the result, also we did some dimension reduction in this case. And for both kind of variants, we feel okay, the result is fine. But when we apply it into the trauma system in US, sorry, in this case we have 72 hospitals, which means actually the dimension is significant increase. So we looking at the result. So we have some conclusion, right? So in this case, you have to do the dimension reduction. So the random forest with the dimension reduction have better performance than the variant without it. But the performance is not good enough to be used actually. So then we think about, we have some observation, and we think the main issue, that is generic surrogate model cannot give you a good, a high or satisfied accuracy for high dimensional problem. So then what shall we do, right? So here we have 2 ideas. The first thing that maybe it is a large problem, it's a high dimensional problem. Can we do some way to simplify the problem, make the very large problem into several smaller problems? So that is the first idea. And the other thing, that random forest is not good. Can we explore some new surrogate model for those problems, right? So that is 2 maybe technique we can use to solve this issue. So here, let's have another example, right? So so feature selection is a very old traditional machine learning problem, right? Actually, but when you looking at that problem with the wheel of optimization, actually, it is expensive combinatorial optimization problem with constraint, because the objective is the performance. If we use the if this feature selection is a kind of classification, we can evaluate the feature subset by training a classifier and calculate the accuracy. So which makes the objective really really expensive, right? Because you need to train classifier. And the other thing that is, so as you know, we only need to do feature selection for high dimensional problem, right? So the decision variable should be 1 or 0 for each feature, right? So actually, the decision variable are binary code in high dimensional. So of course, this problem is easy because the constraint are cheap. You only need to calculate how many features selected. So that's one. It's cheap, but the objective is really expensive, right? Then what shall we do? As I said, actually you cannot use a random forest to approximate the classification accuracy because that is too high dimensional to get a guaranteed accuracy. So then we think actually so in Xidian University, I taught algorithm design, right? So a very basic technique we use, that is divide and conquer, right? That is quite a popular way to simplify the problem, right? When you have a large problem, you can divide it into several smaller problems, and then you can parallelly solve those smaller problems. Then you combine the solution together, then you can solve that large problem. So that is the main idea of this. So here we facing this high dimensional binary code, we use a kind of random grouping way to divide the decision variable into several group. Then we, inside that smaller subspace, we build surrogate model, and we do the search on those smaller surrogate model. Then we combine those solutions together. Then we can have a complete solution. As you know, maybe the random grouping is not correct. Actually, we don't have the budget to determine which solution, which decision variable and which decision variable should be in one same group. That is really expensive. So we can repeat this random grouping several times, right? Then with that, by chance, we can find a good solution. So that is one idea to simplify the problem. Then we think, okay, the feature selection problem, it is one example of single objective, right? So there are a lot of expensive multi-objective combinatorial optimization problem. Then, as you know, you need several surrogate model for each objective. That is really hard. And also for multi-objective optimization problem, the solution is a set of solution. And we have a really low combinatorial budget. So traditional for multi-objective optimization, we care about the convergence and the diversity. So we hope we can have the solution set close to the true parallel front and distribute uniformly or spread the whole parietal front. But in this case, for this in the expensive case, actually you can't to pursue both of those targets. So then we think maybe convergence that is more important than diversity. Then we think and we need really a faster convergence way to get the solution. You know, actually, from my point of view, during my PhD study, I have done many work for multi-objective optimization. The feeling that is, if you use parietal dominance, actually the convergence speed is not fast. But if you use aggregation function, so the convergence is faster. So here, that's the reason why we consider maybe we can decompose this multi-objective optimization problem into several aggregation function, right? And yes, this is not new. So many emo work was done based on that. So, but we think traditional for this aggregation-based emo algorithm, they need a really large number of weight vector, right? So take MOED as an example for 2 or 3 objective optimization problem. Maybe we need 100 weight vectors, but actually in our case we don't need that high diversity, right? Then we think actually for this 2 objective optimization, we only need 3 this vector, and for three objective optimization, we only need 7. With this really rough guidance, we can accelerate the convergence speed. And of course, you know, for combinatorial optimization problem, the parietal front is not have a really good shape as a continuous problem, right? So maybe the weight assignment is not wrong. We cannot equally assign the combinatorial budget to each vector, right? Here we use a kind of Q-learning method to allocate the computation resources. So with this, we can have a really good, really efficient way to get good convergence. Yeah. Here is another example, right? So, you know, in Xidian University, we have a lot of application in circuit design, right? So here is an example, right? Here is a layout. You need to put several items on that layout, right? How to put them to reduce the highest temperature that is problem, right? So if we think about the problem, maybe we should firstly you need to encode this problem into a kind of binary code, right? You give the layout with several grids. So here, this layout we have 100 grid, right? So if there is if one grid has item, so we encode it to 1. If the grid is empty, we encode it as 0, right? So which means actually the decision space is a 100-dimensional binary code, right? And to get the distribution of the temperature field, we need a kind of expensive simulation, right? To get this temperature field. Yes, traditionally, if we solve this problem, we can build a surrogate model from this binary decision space to the highest temperature, right? We can do that, but we feel that is not a good way to do that because we have no that high, the surrogate model, generic surrogate model cannot give you a good accuracy. So then we think anything else we can do that. So we have a lot of deep learning model to do a kind of image to image model, right? So can we model the image of layout to the image of the temperature field as a surrogate model, right? Because actually, in fact, there is some relationship, right? So then after that, we try this. It's really surprisingly the surrogate, this image to image model accuracy is better than the random forest and so on. Then with this, we can do this optimization and we have a really good result. From this, we think actually the mean difference from combinatorial optimization from previous benchmark problem of those continuous problem. Actually, for each combinatorial optimization, they have perform problem domain knowledge, right? So can we use those knowledge to help accelerate the optimization? Yes. Then maybe we think we have two ideas to do that. The first thing that usually those problems have some simulation, right? So those simulation can have different kind of fidelity, right? And if the fidelity level can be controlled by the optimization algorithm, then we can have a kind of trade-off for the accuracy and the cost, right? And also we need to think maybe generic surrogate model is not useful for most of combinatorial optimization problem. Maybe we need to look into those problems to see if we can build some problem-specific surrogate model to help approximate those very hard landscape, right? Okay, so here is some example of simulation, right? So I can give you some example. So usually when you do a kind of simulation, take this example, you need to do a kind of mesh on those that atom. So different kind of mesh will give you different accuracy and cost, right? And also, for example, when you train deep neural network, how many iteration I need, right? So if you have a large number of iteration, you can have a higher accuracy, but it takes longer time, right? So usually, you cannot only use one fidelity level to do that. So if you want a high accuracy, a high optimization performance and low cost, maybe use multiple fidelity level is a good choice, right? So here is an example, right? So I think most of you have done have used evolutionary algorithm to do optimization. You know, at the very beginning of the optimization process, the candidate solution have really poor performance, but with a generation increase, you will have better candidate solution. So we have the idea, maybe at the very beginning, you don't need high fidelity simulation, right? You need to increase the fidelity level during the optimization, right? So it's a kind of increasing fidelity level. But the thing is, when I should increase my fidelity level of the simulation, right? So, so here is the example, right? Well, here is a multi-objective optimization problem, right? So when you do the optimization in the current fidelity level and for several generations, we haven't seen much improvement on hyper volume, right? That is a performance metric for EMO, right? Then, which means actually you have explored the current landscape, right? Which means actually you need to increase the fidelity level, right? So that is a idea, right? Then we can you remember the trauma system design problem? Let's relook this problem. So we know the reason why it is expensive because for each function evaluation, you need to assign many patients to those hospitals. Then you can calculate objective and constraint. And we look the distribution of those patients. We know actually you don't need to allocate each patient, right? You can use a kind of clustering, right? The only fake patient, the center of the cluster can help you to estimate those objective and constraints, right? Actually, which means I can rewrite the objective function and constraint by this, right? So you only need to calculate K patients after the clustering, right? So which means actually this cluster number controls the fidelity, right? If each patient is the cluster center, right? Which means actually you can very accurately estimate those objective and constraints, right? If K is really small, right? Which means you can calculate it really fast, but you have a really low accuracy estimation, right? So which means this K controls the fidelity. And during the optimization, we need to think how to adjust this K, which means how to adjust the fidelity. So the idea that is we can estimate the current acceptable error of surrogate model, right? And then we can have a relationship between K and error. Then with this acceptable error, then we can calculate, okay, currently maybe K1 or K2, that is okay for the current optimization requirement, right? So that is the idea of to dynamically control the fidelity of surrogate models, right? And the last problem I want to introduce you guys is this kind of soft robots design problem, right? So we need to optimize the structure of the robots, and here is a 5x5 robots. We have 25 place to put different kind of material, right, to make it as a robot. So that is structure, right? So this optimization problem that is expensive because to evaluate each structure, firstly you need to run a kind of reinforcement learning based simulation to get the optimal control for this specific robot structure. So actually it is quite expensive. The thing is what things we can do, right? So if you will this reinforcement learning as a kind of simulation, it takes several steps, right? So if you want to save some combinatorial budget, you can stop early, right? But when shall we stop, right? So here, I think at this blue point, it is fine, right? Because we have get the optimal control, and the following step is not necessary, right? So actually, we can learn from those rewards curve to determine when we should stop by detection, that point here. Actually, that is a knee point here, right? Then we can, with this, we can control the simulation fidelity, right? Of course, not for all the robots should have the same number of steps. So we cluster those candidate robots structure, and for each cluster robots in the same cluster, they stop by the same number of steps. So that's one way to cut the combinatorial time. And also we look into the simulation for the reinforcement learning. Actually, as I said, inside the reinforcement learning part, we actually get the optimal control. So that is a kind of actions, right? So we have a kind of assumption, right? So for the robots with similar structure, their optimal action should be similar, right? So if we have a new robot which similar with previous robots, can we just copy the action of the old robots and do this simulation? Then we just do not need to run for the reinforcement learning process. Then we can accelerate the optimization process. Yes, we try this and we have a really good performance. Here is some example of different tasks to optimize the structure of those soft robots. commercial budget is only, I think, it's 25% of traditional algorithm, for example, GA and other algorithm, right? So which means actually this copy the action is a kind of specific surrogate model, right? It is not a generic surrogate model. So usually will give you surprisingly good accuracy. Okay, so that is the very end of my talk. So in fact, the previous work was done by my students. So only 3 PhD students did those work. If you are interested in those work and you want the code, you can find those more information by those link. Okay, I think that is all for my talk. So any question is welcome. We hope we can have some interesting discussion.